In this presentation, we would like to introduce our work, enhancing person synthesis in complex scenes via intrinsic and contextual structure modeling. The advent of generative adversarial nets largely facilitates high-quality image generation. However, generating reasonable persons in complex scenes is still challenging. For example, in the layout-to-image task, the generated persons by the state-of-the-art are not recognizable. We speculate there are several reasons. First, the lack of person structure knowledge. Persons are internally structure-based, despite the size and appearance variety. The structures, such as pose and face keypoints, can indicate the shape, action, and facial expression of persons. The second reason is that person structures are diverse and contextual. The diversity of persons is much higher in the wild. Person poses and appearances change depending on different environments. However, existing approaches directly generate persons along with other objects. In this work, we want to alleviate these problems in the layout-to-image generation task. Our proposed approach, in overview, consists of three parts: person intrinsic structure modeling, contextual structure modeling, and person appearance refining. In person intrinsic structure modeling, we want to model person structures independently. The reason is that, in the layout-to-image scenario, although the context can affect the person's behavior to some extent, persons are actually free to have any pose or face structure as long as they follow some patterns. In our method, we encode person pose and face keypoints into a memory-based model, which is used to maintain the structure distributions. Specifically, we use two autoencoders with a memory bank to save the most representative pose and face keypoints, respectively. Each autoencoder consists of an encoder, a decoder, and a structure memory bank to save the learnt person structures. The memory bank is of size M, which is the number of stored features. In training, given the structure keypoints, the encoded features is compared with the memory bank, and retrieve the most similar ones as the output, then decoded by the decoder. We choose to use the discrete space rather than continuous space is that the layout, as the weak conditions, may not provide enough information to predict from a continuous space. The loss has two parts. One is the MSE loss between the reconstructed keypoints and the ground truth, and another is the L2 distance loss between the encoded feature and the memory bank feature with the nearest distance. In the second part, contextual structure modeling, we want to infer person structures from the context. We represent the layout as a graph, where the nodes are the objects, and the edges are the relations between objects. We then designed a graph convolutional network, or GCN, to model the contextual features of persons. The node features include the object labels, positions and sizes, and the edge features include the relations between objects. In the GCN, we first separately encode the node and the edge features, and then fuse each triples using a MLP, and then use the fused features to update the node features. As a node can be used more than one time, as a subjective or an objective, a final pooling layer is used to aggregate the node features. In the last layer, we only take the person node features as the contextual features, and use them to predict the person pose and face keypoints for the pre-trained memory-based VAE. In the third part, person appearance refining, we map the person pose and face keypoints to their semantic map. The semantic map can be seen as intermediate person representation, which are used to merge with the object semantic maps. The two refiners are based on the fully convolutional network. We then represent our results compared with the existing methods. We first show the qualitative results and then the quantitative results. In the person synthesis quality, we can see that our method can generate persons with reasonable pose structures, appearances, and faces. But the existing methods failed to generate recognizable persons. Our synthesized persons have clear body shapes and facial details. This shows that person keypoints are important for guiding person generation in complex scenes. And the proposed person appearance refiners can successfully convert the person's structural keypoints to semantic parts, such as body, limbs, and faces, to improve person generation. In context-aware person keypoints prediction, our method can infer person keypoints complying with the pre-encoded structures in the intrinsic structure model. The inferred pose keypoints can successfully cope with the context and even other persons. For example, the predicted person poses in the snowfield context in layout A are skiing poses. Layout C mainly includes a motorcycle surrounded by two persons, and the inferred results are riding poses. Layout F indicates two persons with pizzas, and our method can infer two half-body poses near the table. When the layout contains many persons, our method can also generate the crowd reasonably. Thanks to the person refinement modules, our method refines each person separately by generating their intermediate semantic features, which helps generate each person with clear body shape even when these persons are very close or overlapped in the above images. In quantitative results, our method outperforms the state-of-the-art methods in terms of the person-related metrics. Apart from the image generation metrics, use person fit, accuracy, face detection metrics, such average precision and recall, to evaluate the generated persons. This is our work, enhancing person synthesis in complex scenes via intrinsic and contextual structure modeling. Thank you for your attention.